the main part of the actually the computational or hungry part of the DSP. Other part will be done on still in the FPGA, but by the processor. So let's go for the first part. So the main structure of the radar is shown here. We have a transmitter and a receiver. So in this structure, we are considering only one transmit antenna and multiple receive antennas. So the system actually, first, we have an oscillator here, voltage controlled oscillator, that will generate a chirp, which is a sweep in frequency from a duration t, and this will repeat multiple times. And as we see later, we'll explain why it has to repeat multiple times for velocity measurement. This chirp, or this sequence of chirp, will go through two paths. The first path will radiate into the free space, and the second part will go through into the receiver at the input of a mixer. So the radiation will hit a target, as shown here, a vehicle that is going at the speed of v and at range r and at directional or angle of arrival theta, and the echo from the vehicle, will be captured by the antennas, and it will go through the receive signal chain, through the multiple signal chain. For each antenna will be associated with one receiver. The signal chain actually has the signal coming back will be weak, so we will go through a low noise amplifier, followed by a mixer that will receive both the transmit chirp and the receive chirp, and it will generate so-called bit frequency. Then after low pass filtering, it will be digitalized and go through an ADC at given sampling frequency. Then sent the samples will be transported to the DSP unit using a given protocol that we will see later what we are going to use for this use case. So let's move on to the distance measurement. So let's go through the channel, one channel. Let's assume that this is a channel M. We have assumed that we have a target at a range R. The chirp that we sent will be split into two paths. One go to the mixer, and the other one will radiate from the transmitter antenna, hit the target, echo come back. Low noise amplifier will boost the signal. The received chirp will be received after a delay that we've shown here, t, which is with the same shape as the transmit one. Then both the transmit chirp and the receive chirp go through a mixer, and the mixer will generate a bit signal, which consists of the difference between the transmit chirp and the receive chirp. And the difference is a constant, and the difference is for one target, for instance, it's one frequency, and it will be received at a delay t. So let's do some math now. So the chirp slope, which is the bandwidth of the chirp divided by the sweeping time, will be exactly the same as the bit frequency divided by the delay. A round trip, so the EM, when it travels through free space, it goes to the target, it will be bounced back to the antenna, and this will, the distance traveled, it's a round trip of 2r, which is equal to the distance times the speed of the electromagnetic wave, which is 3 times 10 to the power 8 meter per second. Replacing t with its value from the chirp slope, we will get an equation of the range. And you can see that the range is proportional to the beat frequency. Note that the relation between the range and the bit frequency is linear, and the factor beta is just it's dependent of system parameter t and b, and the constant c, of course. So the range to targets is inferred from the frequency content of the bit signal, and using FFT, we can infer the range of a target. And we refer to this FFT as a range FFT. Note that if the mixer is a complex mixer, and then the frequency sampling will be has to follow to meet the Nyquist criteria, 2 times maximum frequency, and if it's complex, will be just greater than the maximum frequency. So assuming now we have a real beat signal, then the FS will be greater than 2 times the maximum beat frequency. And the range, maximum range, will be directly linear to the maximum beat frequency. Replacing just the frequency max here with the FS, or we get an equation that will show what is the maximum frequency that we can, range that we can measure. And as you see, it's dependent of the system parameter t and or the slope of the chirp, and also the sampling frequency. If you want to get a bigger distance, you need to sample fast, which is expected. Now, the second thing that we would like to establish here, what is the range resolution? As we know, the FFT step is inversely proportional to the observation time, or the length of the chirp. And if we differentiate the equation of the range, you can see that the differentiation of the variables here are R and F. So the delta R is proportional to delta F. Again, if we replace the delta F with its value, 1 over TC, we can establish here the range resolution. So what you have to remember from here is just those 2 things, that the maximum range is proportional to the frequency, sampling frequency, and the range resolution is inversely proportional to the bandwidth. Let's move on to the next measurement, which is the velocity. To determine the relative velocity of a moving target, we will need an successive transmitted chirp. And the velocity will be deduced from the phase change reflected of the consecutive chirps that we are sending. Here we are showing a radar frame with n consecutive chirps. Each chirp, of course, has characterized by a sweep time and a bandwidth. So the moving target velocity will be, as for the range, will also be deduced from the FFT over the range, the complex value, the range FFTs that we did before. And we will refer to this FFT as DFFT. And in the frequency domain of DFFT, the peaks will correspond to the phase difference between consecutive chirps. and they are related to the frequency V as follow. So the phase difference can be expressed with time difference, time difference when the echo from the first chirp to the echo to the second chirp, which is delta t. And delta t can be replaced by just the range. And remember that the range over the speed. And remember that the range, it's a round trip, so we have to account twice for the range, or the difference in range between the first chirp and the second. And again, delta R can be replaced by its, since the vehicle is moving at a speed v, and the delta R will be done within the time chirp. So we are replacing delta R with VTC. And remember, again, here, as I said, this is a round trip. So we have to count twice for delta R. So this is the equation of the phase. And from there, we can deduce the speed related to the phase difference. And this C over F0 is just the wavelength divided by 2. And this can be seen as a frequency shift, or it will be referred to also as Doppler shift. So the phase shift is just half the wavelength times the frequency shift. Similar to the range measurement, we are going to see what is the maximum speed that we can actually measure. Since the measurement is phase difference, the phase is bounded between minus pi to pi, and replacing the phase relation with the phase relation with its equivalent. So we will deduce from there that the speed max is just quarter of wavelength divided by the chirp duration. As you see here, the speed max is inversely proportional to the sweep time of a chirp. So if you want to get bigger speeds, maximum speed measurement, you need to have shorter sweep time of chirp. Similarly, the velocity resolution can be deduced. Again, delta FFT is 1 over the observation time, and the observation time here is it's n time the chirp time, so it's the frame time. And differentiating again the speed relation, you see that differentiation of speed is the differentiation of the frequency, replacing the delta F with its equation here, its equivalent. So we will end up with this expression of the resolution. As you see here, the resolution again goes as the observation time is higher, or the frame time is bigger, is longer, the resolution will go, it's better. This is the two equations that we need to remember from this slide: the maximum speed and the resolution of the speed. The third topic, we're going to go quickly, it's the angle of arrival. Angle of arrival requires, in order to do a recovery, it requires more than one antenna. That's the reason our system has more than one antenna, M antennas, for instance. And in the case study we are going to go through, it will be M will be 8. Again, as for the speed, the angle will be deduced also from phase difference along the channels, along the antennas, and it's similar to the velocity. The speed, we are considering successive chirps. So in time, Similarly, for the angle, we are going to do it in space. And then from one antenna to the other, we are going to deduce the phase difference between one antenna to the other. An echo arriving to two successive antennas hit the antennas at different time. And the wave for the second antenna will travel delta R more than the first one. And the relation between the relation that relate the difference in range is related actually to what we would like to measure, which is the directional of arrival or the angle of arrival, which is can deduced directly here from the sine of theta is delta R divided by D. Theta is the same as this. Okay, so the angle of arrival is theta, and theta is exactly the same value. So, and therefore, delta R is just sine theta times D, which is the distance between two antennas. So similarly, the phase difference, as for the velocity, it can be written the phase as related to the delta t, which is the time, the extra time that the wave will take to reach the second antenna. Replacing delta t as in the velocity with delta r divided by c. Remember that this is only delta r. There's no factor of 2. There's no round trip here. It's just delta r. Then we replace delta r with its equation. Delta r is d times sine theta, and therefore we will deduce the relation between theta and the phase. Here we replace d with the half of the wavelength, which is usually it is the case, and this is actually that will give you, that's the value will give you the maximum angle or field of view. And theta can be deduced just like from this relation as the arc sine of the phase divided by pi. As for the range and also for the velocity, what is the angle resolution? Similarly, the delta A FFT or the angle FFT, it's related to the distance here. So it's just the number of antennas divided by 2 pi. That's the step, the FFT step. And if you take this relation phi 2 pi d sine theta divided by lambda 0, which and lambda 0 is the wavelength of the carrier, you differentiate both sides. Delta 3 is 2 pi d differentiation of sine delta theta, just I put it divided here, lambda 0. And as everyone knows, the differentiation of the sine is cosine theta, and we'll end up by replacing d by lambda 0 over 2 to the we end up with a relation that relates the phase resolution to theta. As you see here, the relation for the first time for range and velocity, the relation is linear. Here it's not linear. And the maximum resolution can be get when the cosine is equal to the maximum value, which is 1. And therefore, the cosine 1 was theta equals 0, which is the bore side when the vehicle is in front of the sensors, the antennas, and we'll end up with delta theta 2 over m, and this is radians. As an example, for instance, here, if the number of antennas are 16, you will get approximately in the vicinity of 7 degrees of resolution. If you want to increase the resolution, you have to increase the number of antennas. One other way is to go for the MIMO, where you use multiple transmit antenna and multiple receiving antennas. And the advantage of MIMO, the combination of transmit and receive antenna will be less than the number that you would use for only system with one output, multiple inputs antenna. What we need to remember here, just the resolution of the. So the next, as summarized here, just the velocity and range measurement. As in the system, our system, we are going only to actually use in DSP the main part that we are going to deal with is those two elements. So what we need to remember here is the measurement of the range and velocity it's a linear equation. However, this is not the end of it. In order to identify the actual targets in the presence of noise, further processing is needed to actually do the actual detection of targets. And there are well-known algorithm out there as the constant force alarm or CFAR algorithm that will be performed on the 2D Doppler pins across the M channels. And we are not, this talk will not to deal with the CFAR, as this is will be performed by software. The case study that we are going to go through is it's a system that has 8 antennas. The chirp repetition interval is 24 microseconds. The number of samples in a chirp is 1024, and we are going to consider here that the samples are real and not complex. And the number of chirps is 512. The sample bit width coming from the DAC, this is the DAC resolution, is 12-bit, which is equivalent to 10.5 approximately enob. And there is an inter-frame gap between one scan, one frame to the other. And if you do the math, you will find that this is a short range radar, and it's the range, a maximum range approximately in the vicinity of 20 meters, and the maximum speed will be in the vicinity of 150 kilometers an hour. Let's go through the structure of the bit signal data frame. So the first diagram here shows a scanning, a single channel radar scanning, and this is the multiple scans. There is, for our use case, we have 512 repetition of the chirp in one scan, in one frame, followed by an idle time of 15 milliseconds. The reason that there is those idle times, actually, it's one technique that is used actually to mitigate interferences from the other radars, cross interferences and parallel interferences. So in the digital domain, we are going for one scan for one channel, one scan. We are going to get a matrix of data frame, and this matrix is shown here, and each row of the matrix corresponds to one scan. So the colors actually correspond, the green and the blue here, it's the thing. So the row time is referred to as fast time, and it's and the delta time is the sampling frequency, and on the chirp side, the time is the chirp time. So that's we refer to as a slow time. So we have a slow time and fast time. The frame time is considered to be approximately, there's a typo here. It's 30 milliseconds, 15 plus 15. 30 milliseconds, not 35. And if we go across all channels, we put together those matrices, so we are going to get a cuboid of data. And each one of those matrices correspond to one channel. So the active time for our use case will be between 12 and 15 milliseconds. However, we are going to consider it always 15 milliseconds, and the scan gap is 15 milliseconds, and we are going to consider it always to be 15 milliseconds. So let's go through the skeleton of the system. So the system is constituted of two parts, of course, the transceiver and the DSP. The DSP will be done by a low-cost zinc FPGA 7020 system on chip, and it is coupled with a DDR with a maximum peak rate of 34 gigabit per second. The samples from the transceiver will be transported into the DSP using the CSI2 DeFi protocol. And we will need 4-lane links, or we are going to use 4-lane links. And note that DeFi is source synchronous, and therefore the clock will come with each 4-lane, and there is no overhead coding overhead. And the throughput requirement can be deduced from a simple equation. So it's the sampling rate times 16-bit. Even if it's 12-bit analog to digital an ADC, 12-bit resolution ADC, we are going to pad, the transceiver is going to pad the samples to 16-bit, 0 pad. So the required bandwidth or throughput for each link is 0.7 gigabit per second. Note that DeFi can go up to 2.5 gigabit per second, so we are fine here. What are the DSP tasks? So let's go through this slide and we show the first thing we are going to receive. This is the cube that we are going to receive from the transceiver, and this cube or cuboid this consists for one entire frame across 8-inch channel, and the size is 64 megabit, which is consists just 1024 samples times 512 chirps times 16-bit. The first step is to go through the range DSP, range DFT, sorry, and what we get is range bins. As we show here, we show later as a requirement of the size of the bins is 16 bits. So with 16-bit size, we are going to keep the size of the qubit exactly the same. And since it's real samples, the FFT is symmetrical, and therefore we are going to keep only half of the bins. That's why we have exactly the same size on both before and after the FFT. And what I'm showing here that, for instance, this is just an example, that there is two objects at two different ranges, and we're going to see the peak in the FFT across all antennas. A second Doppler FFT has, as we see later, again, the FFT requirement for the bins, it has to have the dynamic range of 24 bits, and therefore we'll have an expansion of the cube to 96 megabit. And as we see here, the second FFT will discriminate actually in the same range that there is two objects actually, one at speed V1 and one another speed V2. And similar thing in the other range, at range R2, actually there is two distinguished object with different speeds. In parallel, we are going to do another operation. It's integration, and which consists just actually to cross the channel, to accumulate the energy, the power, and keep a list of a given number, programmable, of the in descendant, in given order, descendant or ascendant order, it doesn't really matter. And we are going to feed the cube, the Doppler cube, and this list to a CFR, proprietary CFR algorithm running on the PS to finalize the detection. So we have, just to summarize here, the DSP tasks as a range FFT, followed by DFT in parallel with integration. And the integration here, as I said, is summing the power. So it's a non-coherent integration. So it's not an FFT. We are not taking into account the phase, just summing the power and just keeping it, then keeping it keeping a list in ascending or descending orders, and feeding everything to a CFR algorithm running on the PS. So let's summarize the tasks. Step 1 is range processing, which consists to do 8 times 512 1K point discrete Fourier transform on the received samples. The samples are real valued, and therefore it's symmetrical, as everybody knows. So, and therefore we are going to keep only 512 bins. And to reduce the leakage, we are going to apply windowing to suppress the spectral side lobes. And as a system requirement, we need the FFT bins, we need to have 96 dB range, which is corresponding to 16 bits. The second step is Doppler processing, which is another FFT on the first output, on the output of the first step. So we have a cube, and we are going to apply another FFT. However, this time is along the chirp direction on the chirp indexes, and the number of FFTs is 8 times 512 point discrete transform DFTs. And as for the first FFT, we are going to use also windowing prior of doing the FFT. As a system requirement, we need 144 dB dynamic range for the FFT, which corresponds to 24 bit. And in parallel, we are going to do integration. As I said, we are going along the channel. We are going at the same time doing the processing, the Doppler processing. We are going to do integration, summing up along the channels, the absolute values of cell bins, or the energy actually of cell bins. And as a processing requirement, post-processing requirement, we need only to keep the greatest K parameter, greatest integration in descending or ascending order. So, and the last step is a detection of the target, and this is where CFR algorithm came into play, and this will work on both the step 2 and step 3 output. To summarize, so step 1, 2, and 3 will be done by hardware accelerator, and step 4 will be the task of a processor. Let's go and go through the processing budget. So let's consider frame F. Preceding frame is F1 minus 1, and next frame is frame F plus 1. So as we said, as the system requirement is the active time for the frame is 15 milliseconds, and idle time is for each frame is 15 milliseconds. So the total frame size is 30 milliseconds. So to do the processing, we are going to do on the fly the range processing, and in parallel we are going to do detection of the previous frame as shown here, the green frame. So we start with on the fly doing range processing during the active time of 15 milliseconds, and interscan gap, which is 15 milliseconds, we are going to do 2 parallel processing, Doppler processing, and integration. And detection of the green frame will be done in the next frame time. So the total processing, if you want, of Doppler processing, integration, and detection will be done within 30 milliseconds. And this is actually the steady state. In each steady state, we have Doppler processing, integration, then detection, and at the same time we are doing range processing of the next frame. Note that the range processing here and the detection, they are sharing the bandwidth of the DR, and we have to be careful here. So let's move on to the FPGA architecture of the DSP. So the skeleton architecture is shown here. So there is a PS part and a PL, and the FPGA is coupled to a DDR, SDRAM, with 34 gigabit per second maximum peak throughput, and the sample will arrive through a DeFi link and go through signal processing. It's mainly FFT and integration. A data mover will be responsible of moving data into the DDR through 2 HP ports. 2 HP ports are required, with configured to 64-bit, and the GPU will be will be used to configuring the system. So the main 4 actually subsystem is the DeFi CSS2, data mover, signal processing subsystem, and configuration and control subsystem, plus other maybe filtering. For instance, before going to signal processing, we may use some filtering to filter the cross interferences from other radars if required. So this here I'm showing actually the path for range processing and detection. The red arrows is just doing the FFT and storing the FFT cube into the DDR. And at the same time, we are doing this is the previous actually frame of the Doppler cube. And the Cortex A9 will be working on CFAR algorithm using this cube data. So as you see here, they are both sharing the DDR SDRAM bandwidth. The second step, which is Doppler processing, I'm showing here. Doppler processing, we are going to read the qubit, the range cube, do the FFT and storing it again inside the DDR. So there is a read, and it consists for a read and a write from the DDR. And in parallel, we are going integration. And the integration is just at the end, we are going to store the required list of the integration in the OCM. Note that this OCM is 256 kilobytes, so it's large enough to fit the list. Next, the FFT, we are going the FFT subsystem is based on a FFT processing element, which is using the Xilinx Logic Core FFT V9, a wrapper. We are going to use both this wrapper to do both the FFT of the range and Doppler, and we could use, and it's set, the length is set at 512, and we are going to use complex FFT to do 512 complex FFT to do a real FFT by feeding the odd and the even samples into the I and Q channels of the FFT. At the end, we need to do some combination to get back the bins of the real FFT. So that's why there is a wrap around it. So there's some logic after the IP to do the combining. And the FFT will be preceding the FFT is the windowing. So quickly, the input data width will be 16-bit. The twiddle factor is set at 18 bits. We are using the streaming IO architecture, and we are going to use full precision and scaled. At the end, we are going to truncate or round. And as I said before, the 1024 range FFT will be done using 512 complex FFT. Quickly, the flow of the FFT, it's the FFT will receive a row or a column, depending if it's a range or a Doppler FFT, and it will stream out after a given latency. If we are running it at 200 megahertz, the latency will be 8 microseconds. The FFT will be then generated by the core, and there will be no gap between the bins. So there is only the initial latency. After that, we are going to get the bins one after the other. Quickly, the processing flow here. arrival of the sample will arrive from the interface, D5CSI interface, between one page and the other. So that is one scan and the other will be possibly a gap, and the one page received within 24 microseconds will be fed to a channel FIFO. Here I did two FIFOs for a reason, because we are going to use actually four FFT channel PE. However, for the range FFT, we'll need only one channel. So then we are going to feed the collected samples, the collected page, into the FFT processing element, which is set to 512 point. As I said before, the 1024 real FFT will be done by a complex 512 FFT. 32-bit is just the even and the odd sample of the real samples here. So, and the output will be a complex FFT, and we will need to keep only 512 of the bins, as the other half is symmetrical and it's useless. So, and we will call cross a channel, the 32 byte, a brick. So next step is to write this page by page into the SDM in an efficient way, and we are going to write it in a tiling scheme that we are going to quickly examine here. A brick, as I said before, is 32 byte. So, and and we are going to write those bricks one after the other in a tiled fashion. Instead of writing the bricks linearly in a bank, we are going to, at some point here, we are going to use a modulo, which means so that after 8 bricks in this example, we are going to wrap and change a row inside the bank, and so on. So a tile will hold a page, and if I go on here, each page will be then staggered together, and the whole cube will be written as shown here. Note here, if we would like to access a column, then we need a break from the first tile, the next break from the second tile, and the third break from the third tile, and so on. And the reason doing this is when we activate a row, we are going to activate a row, and we have the possibility to read multiple breaks within one column, one row, sorry. And, and this is before closing the row and moving to the other row. And as you know, in DDR, when we activate a row, so it's better to read access the maximum data in one row. Otherwise, we are going to take a hit each time we move to another row. This is the activation, and we need to deactivate a row or pre-charge, what we call pre-charge, then move to the second row. And this scheme actually will maximize the efficiency of access to the SDRAM. Sorry. Quickly, I will speed up a little bit. I think we don't have time here. The throughput of the interface can be calculated simply. The size of the qubit divided by the active time, and we'll have 4 gigabit per second as a throughput from the interface, and the peak DDR access rate is 34, approximately 34 gigabit per second. And however, the effective transfer rate is a peak rate times storage scheme efficiency. So, and this is depend how you are writing the data. So with 70%, if we consider that our scheme give us approximately 70% DDR access efficiency, we'll still have approximately 19.5 gigabit per second available for the software tasks. Note that both the range processing and detection are accessing the DDR. So we have approximately 15 milliseconds with almost 20 gigabit for bandwidth reserved for the software to do the CFR processing. I will go a little bit fast here, just I will speed up here. Similarly, for the Doppler processing, we are going to read the qubit from the SDR, feed it to the FFT. However, we will need 4 channels in order to keep up with, in order to be able to complete the task of Doppler FFT within the 15 millisecond. So, and we are going to do it page by page. So we are going to read the page, do FFT, write the page, read the second page, and so on. However, we are going to overlap the reading and the FFT processing. So quickly here, we will need actually to keep up with the to do the task within the constraint of 50 milliseconds. We will need actually 2 ports of HP port at configured at 64-bit and running at 200 megahertz. Quickly here to show how this will work, we will read the page. We are going to process the FFT. However, within the FFT time, we are going to read in parallel the second page. We are going to write into the output writing in the FFT, output FFT will be done here, and we are going to write to the SDRAM and start another cycle. So this cycle actually is the steady state. We will have 2 constraints here in order to fit within the constraint of 15 milliseconds. We need the steady state time times 512. Number of pages has to be under 50 milliseconds. At the same time, the read time from the SDRAM has to be less than the latest FFT and the output, the time to write into the output FIFO. If we have the assumption and do the math, the peak rate for the DR34, the efficiency of the DR is assumed to be 70. The HP port that I pick is 74, operating frequency 200, and the latency from the IP, Xilinx IP with 512 is 8 microseconds, and it's running at 200 megahertz. So we will meet our constraint of a read time of the page will be less than the processing time of 1 page, and the total Doppler processing within time budget. So the architecture will actually fit our requirement. Finally, let's take a look if what is the FPGA utilization. So the main part actually will consume more real estate is the FFTP. It's consuming around a quarter of the LAT and registers and BRAMs and half of the DSPs. Both DeFi and data mover consume about 10% of the LAT and for each and the registers. The total of these 3 subsystem, it's 50% of the DSP, approximately 50% of the LATs, and a third of the BRAM racks. Note that we will need on top of that, of course, the configuration subsystem, which is not accounted here, and possibly filtering, cross interference filtering, which will consume some other resources. So this will end up my talk. So I'm open for questions. I'm really sorry I went over the 45 minutes talk, Mike.
No problem, Bashir. It was fantastic. We did get a couple questions during the presentation, but they were not about the details of your talk. They were more about making sure that they could get access to the webinar recording afterwards. I think everyone was enjoying what they were hearing. So if anyone has questions, feel free to post it. If not, of course, please feel free to reach out to Fidus. We'd be happy to discuss questions, projects in detail, or answer and dig into this a little bit more. Bashir, thank you very much for this very good, very detailed presentation. I enjoyed it. I'm certain that others enjoyed it as well. At this time, I'm going to end the webinar, and if anyone would like to follow up, please feel free to reach out. Thank you again.
Thanks, everyone. Goodbye. Thanks, Max.
Bye for now.